Hi everyone, welcome to Maths World UK. I'm James Grime and today I'm speaking with Sarah Hart. Sarah is a mathematician from Birkbeck, University of London, and today Sarah is going to talk about the maths of music. In fact, she's going to talk about how they designed the octave. Now, Sarah is also the Professor of Geometry at Gresham College. That's a very fancy title, and it means that she does a lot of public talks. So if you like this, and I think you will, and you want to see more of Sarah's talks, they're all available online, and we'll give you details of that at the end of the video. But before then, I started my conversation with Sarah by asking her, what do you need to become a mathematician?
The biggest thing you need to be a mathematician is to kind of be okay with failing a lot, because that's what you do. If you're trying to solve a problem, you try it this way, it doesn't work, you try it that way, you don't understand, you try it for like a really small number. Can I do it when, n equals 2? No. Can I do it when n equals 2 and it's a really, really special case? And eventually maybe you can do that tiny weeny thing and then you build on that. And if you think of that as just, which is what it is, kind of playing, you're playing and just seeing what there is and what's going on, and let's try this, and it's like a fun puzzle. It takes a while, and then sometimes something will just click together and you'll be like, okay, right, it's all about this thing, and then you make some progress.
It's a little bit like music in that way, isn't it? So you have to practice, you have to get better at it. It's not just about talent, and that's my segue into what we're talking about today.
Absolutely, yeah. So yeah, there are lots and lots of links between maths and music, and even from the very basic, the rhythms of a piece of music, the beats, the regularity, the patterns there, you've got bars and things like that, repeating patterns. When you're singing, you might have, repeating tunes in the verses and the choruses of a song. And so there are symmetries there. You can do mathematical transformations, like you can translate notes up or down and transcribe things, or you can maybe reverse them or have echoes. And if you ever played any Bach music, you see all these kinds of patterns that are happening. But as well as that, there's actually mathematics behind sound itself. So I wanted to talk a little bit about some of that with you and sort of reveal that there's a hidden mystery at the heart of the piano keyboard, which we're going to explore. But to begin with, I'm going to show you a very, very simple instrument. This is an extremely simple instrument. It's called a siren whistle. And this is going to help us to understand something about frequency. So when we make a sound, if it's not just random white noise, if it's a defined particular pitch, a particular note, then that's because there is a repeating sound that happens over and over again, and it has a certain frequency. That's what gives it a pitch. And we can see the link between frequency and pitch with this little instrument. So inside here, there are two discs. There's one disc that is fixed, and there's one disc that can move. And those discs are perforated. They've got little holes regularly around them. When the holes of the two discs line up, then the air can go through. And if they don't line up, then they're not going through. So when I blow into it, the disc that can move will start rotating. And if I blow hard, then it will rotate rapidly. When I stop blowing into it, then it starts to slow down. So when the disc is rotating rapidly, the air is going at high frequency through. It'll have regular pulses, and those have a high regularity, a high frequency. And as it slows down, the frequency will decrease. So you can hear what happens to the pitch of the sound right at the start, and then as it slows down. So okay, I've stopped blowing on it now, and you hear that sound is just going down and down. It's lower and lower and lower. It's getting quieter too, but it's getting lower. So we can say already that the higher the frequency, the higher the pitch. Now, we could be a bit more specific about that. So it's a second little instrument. This is so it fits onto the camera. I have got a guitar, but this is a ukulele that my daughter painted butterflies on for reasons. Who knows? So here, we've got a little ukulele, and it's got strings, and you can make a sound by plucking the string. So people have been doing experiments with sound for a long time. Pythagoras did experiments not with ukulele, but he had a very simple instrument called a monochord. So mono, one chord string. So it's like one string, very simple stringed instrument. And he found that if you pluck a string and then if you make it shorter, say here, so I've just put my finger on here to make it a shorter string. So now I've just got this shorter bit. So you get another note and it's higher up. Okay, so shortening the string raises the frequency. it raises the frequency, it raises the pitch. And we now know, actually, we've got various laws that are called Mersenne laws, after Mersenne, who we may know better from Mersenne primes, but he also did a lot of work in the mathematics of music, that tell us exactly what's going on. So the first one of these, the one that's relevant to us, is that the frequency that a string makes is inversely proportional to its length. In other words, if you halve the length, you double the frequency, something like that. There are some other things. So the other couple of laws about frequency with strings. One is if you have a thicker string, so if you sort of change its what's called linear density, the mass per meter, if you make it thicker, then the pitch will go down, the frequency will go down. And you see that with like a guitar, some of the strings are thicker than others, and that's why, so that you want lower notes, you have a bit of a thicker string. And the other one is about the tension in the string. So when we're tuning a stringed instrument like a guitar or this ukulele, if you tighten these screws at the end, so you're making the string tauter, you're increasing its tension, that raises the frequency. But it actually raises it in line with the square root of the tension, not with the tension itself. So the frequency is proportional to the square root of the tension. And that law was found by a lute maker in Italy in the, I guess, late 15th century. And his name was Vincenzo Galilei. He was Galileo's father. And this law about frequency being proportional to the square root of the tension, that's believed to be the first square root relationship that we know of. So, gravity has an inverse square law. This is a square root relationship. And that, anyway, Galileo's father found that. So thank you to him. So what did Pythagoras find? So he was doing these experiments with the frequencies of strings, and he found that with some changes in length, you get sounds that are pleasing together. So the most simple of these is if you take your string, and then if you make it half the length, so you halve its length, which is about kind of there. So if I halve its length, here's the original one, and now it's not very good because it's a ukulele, but those sound very similar to each other. And we call that now, we say it's an octave gap, an octave interval. Those sound very similar, almost. So if we talk about singing in unison, even, we're usually not singing exactly the same note. Like if it's a mixed group, the men will be singing an octave lower than the women. We still call that unison singing. So those are very similar and pleasing together, almost the same sound. Another nice relationship is if you take 2/3 of the way along the string. So it's, we can sort of guesstimate, it's about here, right? It's about 2/3 of the way from here to here. If we play that one, so here's the original one. Those two notes sound nice together. We call that a fifth nowadays, a perfect fifth interval. It's the first two notes of Twinkle, Twinkle, Little Star, for example. They begin like that. So that's kind of, you hear those in chords. And another one is if you take 3/4 of the length. So here's your note. Here comes the bride, or some things. That's called a perfect fourth. And these relationships, these very nice, simple fractions of a half, 2/3, 3/4. This is exactly like the Pythagoreans love this stuff. They believe that, simple mathematical relationships were behind the beauty of the universe and the harmonies that we hear. And this music, half, 2/3, 3/4, those relationships, they really like that. And they said, of course, this is how the universe is set up, that it's all about beautiful number relationships. So they knew these things. And so I've got another tiny instrument here, all miniature instruments. This is my miniature keyboard to show you on a camera. I wanted to show you why these things, I've said octave and I've said fifth and I've said fourth. So what's that got to do with these 2/3 and so on fractions? Well, on a keyboard, you can see, if I just play this note here, which is called a C, you could turn the volume up a tiny bit. Then this, if we have this as our starting note, if we go up one octave, as I've called it, so those sound nice together. I discovered yesterday, this is a dry wipe keyboard, clearly meant for telling people things. Let's say this is frequency 1, and then we double the frequency. So that's now doubled the frequency. So why is it called an octave? Because 1, 2, 3, 4, 5, 6, 7, 8, it's the 8th note. Okay, so that's why oct 8. What about this fifth I talked about? So that's when you have 2/3, you're multiplying the string length by 2/3. So remember, it's inversely proportional to the frequency. So string length 2/3 means frequency times by 3 over 2. Okay, so that's my, it's twinkled, right? That's my fifth. So 1, 2, 3, 4, 5, that's y. And we've multiplied the frequency by 3 over 2. There we go. So that's now, we're building up our keyboard. That's my fifth. If I wanted to go up, we can combine them. So remember a fourth, what was that? I said that was when the string was 3/4. So flip that upside down, 4/3 would be what happens to the frequency. So if we went up a perfect fourth, so that's fourth. So there's my 4/3. We won't fill in every note on the piano. But if I do a fifth and then a fourth, we've got to multiply these two together. So I'll go up a fifth and then I go up another fourth. I've got to multiply that 3 over 2 by 4/3. And if you do that, you get 12 over 6, which I believe is 2. And that's exactly what happens. And there's your fourth. So if you go up a fifth and then a fourth, it all works nicely. So you can sort of multiply these things together. Now on the piano, obviously there are lots of notes. And we divide our octave, so going from here to here, we divide that into actually 12 little subdivisions. They're called semitones. So these are where the black notes come in, and they're all just these equal divisions. Okay, so there are 12 of those. Now why? That's the question. Why are there 12 notes in an octave? And if you go to a piano key, not that little tiny one, but a full-size piano, you'll see that there's a relationship between this 12ness and between fifths. Because if you, I'll just show you this, the start of it. If you start at a very, very low note like this one, this happens to be a C, but it doesn't matter. If you go up by fifths, and then you do it again, and if you do it again, and if you do it again and again and again, eventually you start hitting black notes, that's fine. If you keep going, after you've done 12 of these, the next one is another one of these, it's just a lot higher. And it's actually 7 octaves higher. So you've done this doubling of frequency 7 times. And that all works nicely on a piano. But there's a problem. And the problem is, when Pythagoras was trying this with strings, he had these monochord things. So the legend says that he's got these 2 monochords, and one, he did this halving thing. So he halved the string length 7 times. And that means you've doubled the frequency 7 times. And so you've got 7 octaves. You've gone up 7 octaves. So you get a high note there. So he did that. On the other monochord, he started with the same length of string initially, and then he was going up in fifths. So he was increasing the frequency each time by 3 over 2, which is like two-thirdsing the length. Not very grammatical there. I did that 12 times. And so having seen this thing on the piano, we expect we get the same note. But we don't. We don't quite get the same sound. They're just a teeny bit annoyingly different from each other, which is very disconcerting for the Pythagoreans, who wanted everything to match up all nicely. And so they wondered, can we do this with other gaps? So 12 fifths isn't quite, it's very close to, but it's not quite 7 octaves. Are there other subdivisions? And they even explored things like dividing the octave into 31 or 53. Imagine learning your scales. If there were 53 notes in a scale, it's just horrible to bear thinking about. But we can see what the problem is. I'll just write tiny little thing down. Look, here's my makeshift board here. So what we're doing, if we've got our initial frequency, right, and we're going up by octaves, then we're gonna, at each point, we're gonna double the frequency, right? So that's going up 1 octave, and we want to go up by 7 octaves. So we're actually going to be doubling 7 times. We've got a 2 to the power 7 there. So we'll end up at 128, that's 2 to the power 7, times our original frequency. That's going up 7 octaves. On the other hand, if we want to start off with our frequency and we go up by these fifths, so that time, each time we're multiplying by 3 over 2, and we're doing it 12 times. So we do 3 over 2 to the power 12. And already it looks implausible that we're magically going to end up, and we don't. And it's I'll give you a rough, it's about 129.7 times our original frequency. So these numbers are not the same, right? And they're different enough that human ear can easily detect and find that a horrible, horrible pair of sounds listened to together. Now, the problem is, you can say, well, maybe just keep going until we find a pair that do match up. Maybe it's not 12 and 7, maybe it's something else. The problem is, if you were going to do this, you'd have to have this 2 to the 7 doesn't equal 3 over 2 to the power 12. But if you had 3 over 2 to the power I don't know, A equals 2 to the power B, say, if you just kind of multiply up by the 2's here, then this would imply that 3 to the power, so this implies that 3 to the power A would equal 2 to the power A plus B. Now that you can't do that. I mean, if A and B are, positive whole numbers, that doesn't work. The thing on the left is odd and the thing on the right is even. And so they can never be equal. However high you go, 53 notes in a scale, it's not going to work. So it can't ever work, which begs the question then, how are we doing our piano keyboard? How does the piano keyboard have beautiful divisions into 12 exactly equal things? So what you would need for that to happen, and it took people a long time to get to this position, because the basic problem is, if you want all of your little 12 things to be, starting here, from here to here has to be the same as from here to here, and then all of these the same, then you'd need, this is what you would want, I'll just write on the other side of this, this is what you want some frequency change, like a 3/2, but not that. You'd want to do this 12 times and get an octave. So in other words, you'd have to have some number x where x to the power 12 is 2. Now, to our modern eyes, there's no problem with that. You just say, okay, x is the 12th root of 2. Job done, let's go. But if you're 500 years ago, that is really not what people want. It's a number that can't be expressed as a fraction. It's a so-called irrational number. And these are viewed with suspicion, of great suspicion. And it's not one that's nice to make. So you can make something like the square root of 2. It's just the diagonal of a unit square. That, at least you can construct that geometrically. The 12th root of 2 is just like, what even is that? People just did not like it. They didn't like either that you had to kind of compromise on your lovely perfect fifths. These things are now not producing exactly 3/2. The octave is fine, but everything else is just tweaked a little bit. It's tempered down. It's made a bit smaller. We talk about temperament with pianos, equal temperament, and this is what you have to do. You have to make a little compromise. But it does work very well, and it means that keyboard instruments can be tuned so that you can change key and you don't have all these kind of problems and things not quite matching up at the ends. So this is what we now do, this thing called equal temperament. Every semitone is exactly the 12th root, well, I say, it's some very good approximation to the 12th root of 2 times the previous semitone. That's why we can get the circle of fifths and everything matching up on the piano. So I just want to tell you one more tiny thing about this, because I've got a slightly bigger instrument here just to show you something. This is a guitar. It's a bit bigger, and I wanted to show you, look, on the guitar, or even on a ukulele, you've got the different notes. So each of these little pieces is you going up one semitone. So you can start here, and then every one of those is one semitone. So they're equally spaced notes, but they're not equally spaced. Look, these are much closer together and much further apart at the top. So they're supposed to be equally spaced notes. What is going on there? We've just seen that, it's all supposed to be about the 12th root of 2. Well, what is going on is, and let's have an approximation that isn't quite the 12th root of 2, but it was the one that Vincenzo Galilei recommended to lute makers everywhere. 12th root of 2 is but this number 18/17, that's at least a nice fraction. Okay, so you can easily construct that without any complicated mathematics if you're making a lute or other stringed instrument. 18/17 agrees with the 12th root of 2 to 4 significant figures, so it's a good approximation. So what we'll do, I'll just bring back my little ukulele because you can show the whole thing. So what you do is, so 18/17 for the frequency, that means the length needs to be 17/18. We turn it upside down. So in order to go at one semitone, I take my original string, and where do I put my first fret? It's an 18th of the way along. But then to get my second fret, it's not an 18th of the original distance, it's an 18th of the new slightly shorter distance. So you get this sort of geometric progression thing happening, and then each step it's an 18th of the new shorter distance. So as you keep going along and along, you're just taking proportions. It's because it's proportions and not, adding. So that's why the frets get closer and closer together, even though the notes are equally spaced. So that's basically what I want to say, just a tiny bit of an insight into the relationship between mathematics and sound.
That was brilliant. I didn't know a lot of that. And before we finish, is there any, where could we find more of your lectures?
Well, thanks for asking. So this year I've got this Gresham professorship role. It's a 3-year role. Each year I do 6 public lectures, and the lectures this year have been 3 of them have been about maths and music. So those might be particularly of interest. And I think you're going to put a link to that underneath the video. And then the other 3 have been about mathematics and literature and the relationships there. And then the one I did just recently, most recently, is about the history of like mathematical symbols, why we use the numbers we use, what, you know, who invented the equal sign, where did 0 come from? So if you ever wondered about any of those questions, then you can check those lectures out. And then, of course, next year I'm talking about maths and art and lots of other exciting things.
Thanks, Sarah. And like Sarah said, we will put a link to her public lectures in the description. So I guess that's all for now. So I'll say thank you for watching. Stay curious.